Tonight, we're going to explore one of the strangest and most beautiful contradictions in all of astrophysics. A massive star dies, its core collapses, the outer layers detonate, and a supernova explosion hurls everything outward with such violence that it briefly outshines an entire galaxy. And then, from deep inside that explosion, something impossible seems to happen. The dead remnant, the crushed core left behind by the star that just destroyed itself, starts pumping energy back into the blast. Not a little energy. Enough to make the supernova 10, 50, even 100 times brighter than it should be. The corpse of the star is somehow making its own funeral more spectacular. How is that possible? How can something that has already died make the explosion that killed it even more powerful? That's exactly what we're going to uncover tonight. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something fundamental. Stars are not eternal. They feel permanent when you look up at the night sky. The same constellations that guided ancient sailors still hang in the same positions tonight. The same stars your grandparents saw are the same ones you'll see when you step outside. But that permanence is an illusion created by the mismatch between a human lifespan and a stellar one. Stars live for millions or billions of years. We live for decades. From our brief perspective, stars seem frozen in time, but they're not. Every star that shines in the sky is slowly dying. It has been dying since the moment it was born. Because what a star really is, at its heart, is a battle. A war between two fundamental forces that has been raging since the star first ignited. On one side, gravity, the relentless inward pull of all the star's mass trying to crush itself down into the smallest possible space. Gravity never stops. It never weakens. It never takes a break. It has been pulling inward since the cloud of gas that formed the star first began to collapse. And it will keep pulling until the star has nothing left to fight back with. On the other side, radiation pressure. The outward push generated by nuclear fusion in the star's core. When hydrogen atoms are fused into helium under the extreme temperatures and pressures at the center of a star, the reaction releases enormous amounts of energy. That energy radiates outward through the star, creating pressure that pushes against gravity's inward pull. And for most of a star's life, these two forces are perfectly balanced. Gravity pulls in. Fusion pushes out. The star holds steady, shining, stable, existing in a state of equilibrium that can last for billions of years. Our sun is in this state right now. It has been fusing hydrogen into helium in its core for about 4.5 billion years, and it has enough fuel to keep doing so for roughly another 5 billion. During all that time, gravity and radiation pressure have been locked in their slow-motion wrestling match. Neither one gaining ground, neither one giving it up. The sun shines steadily because of that balance. But here's the critical point. The fuel is finite. The hydrogen in a star's core doesn't last forever. And when it starts running low, the balance shifts. What happens next depends entirely on how massive the star is. For a star like our sun, the end is relatively gentle. When it runs out of hydrogen in its core, it will swell into a red giant, shed its outer layers into space as a beautiful planetary nebula, and leave behind a dense, Earth-sized remnant called a white dwarf. No explosion, no drama. Just a slow, quiet fading over trillions of years as the white dwarf radiates away its stored heat and cools into darkness. But for massive stars, stars born with more than about 8 times the mass of our Sun, the story is profoundly different. These stars don't go quietly. They can't. Their enormous mass and the fierce gravity it produces drive them through a sequence of nuclear reactions that smaller stars could never achieve. And at the end of that sequence, instead of fading gently into the night, they detonate. Let's follow one of these stars to understand why. Imagine a star 20 times the mass of our Sun. It burns through its hydrogen fuel far faster than the Sun does. While the Sun will burn hydrogen for about 10 billion years, a star this massive might exhaust its hydrogen supply in just 8 to 10 million years, roughly 1,000 times faster. Massive stars are the gas guzzlers of the cosmos. They burn hotter, shine brighter, and die incomparably younger. When the hydrogen in its core runs out, this massive star doesn't simply stop fusing. Instead, something remarkable happens. The core contracts. Without hydrogen fusion pushing outward, gravity wins temporarily, compressing the core until the temperature and pressure become high enough to ignite a new fuel: helium. Helium nuclei begin merging into carbon and oxygen. The star has found a second wind. It stabilizes again, burning steadily, holding itself up against gravity once more. But helium burning doesn't last as long as hydrogen burning did. The star chews through its helium in a fraction of the time, perhaps a few 100,000 years. And then the core contracts again, temperatures rise further, and carbon begins to fuse into neon and magnesium. This stage lasts maybe 1,000 years. Then neon fuses into oxygen and magnesium. That lasts roughly a year. Then oxygen fuses into silicon and sulfur. That stage lasts a few months. Do you notice the pattern? Each new fuel source is consumed in a shorter and shorter time. The star is racing through its nuclear options at an accelerating pace, like someone burning through their savings faster and faster. Hydrogen lasted millions of years. Helium lasted hundreds of thousands. Carbon lasted thousands. Neon lasted roughly a year. Oxygen lasted months. The star is running out of tricks, and it's running out fast. And then comes silicon. Silicon fusion is the final act, the last fuel source the star will ever burn. Silicon fuses into iron in the core of the star, and this happens extraordinarily quickly. A massive star can burn through its entire silicon supply in roughly 1 day, 24 hours. After millions of years of existence, the final chapter of nuclear fusion takes less than a single day. By this point, the star has developed a structure that astronomers sometimes compare to an onion. Layers upon layers, each one composed of different elements, nested inside one another. Hydrogen on the outside, then helium beneath it, then carbon, then neon, then oxygen, then silicon, and finally at the very center, a core made entirely of iron. Each layer represents a different chapter in the star's life, a record of every fuel source it burned through on its long march toward death. But iron is where everything comes to an end. And this is one of the most important facts in all of astrophysics. Iron is the dead end of nuclear fusion. Here's why. Every element lighter than iron releases energy when it fuses. Hydrogen fusing into helium releases energy. Helium fusing into carbon releases energy. Carbon, neon, oxygen, silicon, all of them release energy when they fuse into heavier elements. That released energy is what creates the outward radiation pressure that holds the star up against gravity. Fusion has been paying the star's energy bills for its entire life. But iron has the most tightly bound nucleus of any element. To fuse iron into something heavier doesn't release energy. It absorbs energy. It takes energy away from the star instead of providing it. Fusing iron is like trying to wring water from a stone. You can squeeze as hard as you want, but you won't get anything useful out of it. You'll only waste your own effort. Iron sits at the bottom of the nuclear binding energy curve, and nothing the star can do will extract usable energy from it. This means the iron core is inert, dead weight. It sits there at the center of the star, growing larger and heavier as more silicon in the surrounding shell fuses into iron and deposits itself onto the core. And the iron core produces absolutely no outward pressure. For the first time in the star's entire multi-million-year existence, gravity has no opposition in the core. Nothing is pushing back, and the core is getting heavier by the second as fresh iron accumulates from the shell above. This can't last, and it doesn't. When the iron core reaches a critical mass, roughly 1.4 times the mass of our Sun, a threshold known as the Chandrasekhar limit, something catastrophic happens. The core can no longer support itself against gravity. The electrons that have been providing a quantum mechanical resistance to compression, a phenomenon called electron degeneracy pressure, are overwhelmed. They're forced into protons, creating neutrons and releasing ghostly particles called neutrinos. The core loses its structural support almost instantaneously. And then the core collapses. Not slowly, not gradually. The inner core plunges inward at speeds approaching a quarter of the speed of light. In less than a single second, a core roughly the size of Earth is crushed down to a sphere roughly 12 miles across. The width of a small city. Think about that transformation. An object the size of a planet compressed to the size of a city in a fraction of a second. The density becomes so extreme that a single teaspoon of this material would weigh about 4 billion tons on Earth. Roughly 8 times the combined weight of every human being alive on the planet today, compressed into the volume of a sugar cube. What's left at the center is a neutron star, a ball of matter so dense that it exists at the edge of what physics can describe. And we'll come back to this neutron star later, because it turns out to be the key to our entire mystery. But for now, the story is about what happens to everything else. The outer layers of the star, those onion-like shells of silicon, oxygen, carbon, helium, and hydrogen, don't know what's happened yet. Information can only travel at the speed of light. And the collapse happens so quickly that the outer layers are still suspended in space, oblivious, with the floor suddenly pulled out from under them. They begin to fall inward, chasing the collapsed core, accelerating under gravity, but something stops them. When the inner core reaches nuclear density, the density of an atomic nucleus, it becomes essentially incompressible. It stiffens violently and rebounds, bouncing outward like a rubber ball that's been squeezed too hard. This bounce sends a powerful shockwave racing outward through the infalling material. At the same time, the collapsing core releases an almost incomprehensible flood of neutrinos. These particles carry away roughly 99% of all the gravitational energy released by the collapse. 99%. The visible explosion, the flash of light that we see, the blast that tears the star apart that represents only about 1% of the total energy released. Most of the energy escapes invisibly, carried away by neutrinos that pass through matter almost without interaction. During a supernova, trillions upon trillions of neutrinos would pass straight through your body without disturbing a single atom. The shockwave initially stalls. It runs into the dense, infalling material above the core and loses energy, like a wave crashing into a seawall. For decades, this was actually a problem in astrophysics. Computer simulations struggled to get the shock wave to successfully blow the star apart. It kept stalling, failing to reach the surface, but a small fraction of those neutrinos, somewhere around 5 to 10% of them, deposit their energy into the material just behind the stalled shockwave. This energy revives the shock. The shockwave surges outward again, accelerating, ripping through the outer layers of the star, tearing them away from the core and flinging them into space at speeds of 10,000 miles per second or more. This is a core collapse supernova, and when it happens, for a few weeks, a single dying star can outshine an entire galaxy containing hundreds of billions of stars. The explosion is so bright that it can be visible to the naked eye even from enormous distances. Historical records describe supernovae that appeared as brilliant new stars in the sky, shocking observers who believed the heavens were unchanging. Chinese astronomers recorded one in 1054 that was visible during daylight for 23 days. That supernova created the Crab Nebula, which we can still observe today, nearly 1,000 years later, still glowing, still expanding, a monument to a star that died before the Norman conquest of England. The material flung outward by the explosion is called the ejector. It's a violently expanding cloud of gas carrying with it all the elements the star forged during its lifetime, plus new elements created in the extreme conditions of the explosion itself. This expanding cloud of debris is what we see shining when we observe a supernova in the weeks and months following the blast. But here's the essential question for our story tonight. What makes the ejector keep glowing? After the initial flash of the shockwave breaking through the star's surface, what keeps the expanding cloud luminous for weeks and months afterward? The answer, for ordinary core collapse supernovae, is radioactive decay. During the explosion, extreme temperatures and pressures forge a specific unstable isotope called nickel-56. This isotope is radioactive. It decays into cobalt-56 with a half-life of about 6 days. Then, the cobalt-56 itself decays into stable iron-56 with a half-life of about 77 days. Each decay event releases energy in the form of gamma-ray photons. These gamma rays are absorbed by the surrounding ejector, heating the gas, keeping it luminous. The supernova continues to shine because radioactive material embedded within the expanding debris is steadily releasing energy, like a slow-burning chemical fuel tucked inside an expanding lantern. And this process is beautifully predictable. Radioactive decay follows strict mathematical laws. If you know how much nickel-56 was produced in the explosion, you can calculate exactly how bright the supernova should be at any point in time. The brightness follows the decay curve of cobalt-56 with remarkable precision. After 77 days, half the cobalt-56 has decayed. After another 77 days, half the remaining half has decayed. The light curve, the graph of brightness plotted over time, traces this exponential decline almost perfectly. For most core collapse supernovae, this is exactly what astronomers observe. The supernova brightens rapidly as the shockwave breaks through the stellar surface. It reaches a peak, and then it fades, following the predictable cobalt-56 decay rate, dimming steadily as the radioactive fuel is spent. Within a few months, the supernova has dimmed dramatically. Within a year or two, it's a pale shadow of its former brilliance. Eventually it fades beyond the reach of any telescope, leaving behind nothing visible except an expanding shell of enriched gas. The show is over. The curtain has fallen. This is the expected story. The star explodes. The ejecta glow from radioactive decay. The light fades on a strict schedule dictated by nuclear physics. There's nothing left to add energy. The star is dead. The nuclear fuel is spent. The radioactive elements are decaying away. With every passing day, less energy is released. The supernova grows dimmer. The light fades. Everything proceeds exactly as the physics demands, except sometimes it doesn't. Because starting in the early 2000s, astronomers began discovering supernovae that refused to follow the rules. Supernovae that were astonishingly, almost absurdly, luminous, not a little brighter than expected, 10 times brighter, 50 times brighter, in extreme cases, up to 100 times brighter than anything radioactive decay could possibly account for. Astronomers named them superluminous supernovae, and they remain among the most powerful explosions in the known universe. To appreciate how strange these events are, consider what the word superluminous actually implies. A regular core collapse supernova is already one of the most violent events in nature. It already outshines an entire galaxy for a brief time. Calling something superluminous means it exceeds even that extraordinary standard by a vast margin. It's like finding a bonfire that somehow burns brighter than a forest fire. The underlying physics should set a ceiling on how bright a supernova can get, and superluminous supernovas smash through that ceiling as though it doesn't exist. Astronomers weren't just surprised. They were confronted with explosions that seemed to violate the energy budget of a dying star. One of the earliest widely recognized examples was discovered in 2005. It peaked at a luminosity roughly 300 times greater than a typical core collapse supernova. Astronomers checked their instruments. They re-examined their data. They looked for errors, but the observations held firm. This supernova was radiating far more energy in visible light than any plausible amount of nickel-56 could produce. To generate that much light through radioactive decay alone, the explosion would have needed to forge an absurd quantity of nickel-56, many times more than the total mass of the star's core. The numbers didn't add up. They couldn't add up. Something else was feeding energy into the explosion. Some additional source, hidden inside the expanding debris, was powering the supernova and sustaining its brilliance long after it should have faded into obscurity. Since that discovery, astronomers have found dozens more superluminous supernovae. Each one defies the conventional model. Some stay luminous for months longer than expected. Others reach peak brightnesses that rival the combined output of 10 billion ordinary stars. And the critical question, the question that now drives an entire field of research, is simple and profound. Where is the extra energy coming from? Because remember, the star is dead. Its nuclear fuel is spent. The core has collapsed. The explosion has already happened. By every conventional measure, there should be no new energy being injected. The ejector should be coasting outward on momentum alone, slowly fading as the radioactive nickel and cobalt decay away on their fixed schedules. There's nothing left inside to burn, nothing left to detonate, nothing left to power anything. And yet, these supernovae keep shining. They radiate energy in quantities that dwarf what radioactive decay can deliver. Their light curves don't follow the cobalt-56 decline. They stay elevated. They plateau. Some of them even brighten again after an initial dip, as though something inside is waking up, revving its engine, pouring energy into the debris from behind. Imagine you're watching a campfire. The logs burn, the flames leap and dance, the heat washes over you. But as the wood is consumed, the fire dies down, the flames shrink, the embers glow orange, then red, then dim. This is what a normal supernova does. The fuel is used up, and the light fades on schedule. Now imagine that same campfire, and just as it should be dying down to grey ash, it suddenly flares back up. Brighter than before, far brighter than it ever was when the logs were burning. With no new fuel added, no fresh wood tossed on. Just the ashes somehow producing more heat and light than the original fire ever did. That's what a superluminous supernova is doing. And it makes no sense unless something inside the explosion is acting as an engine, something created by the explosion itself, something that is, against all expectation, pumping energy into the expanding debris long after the star has finished dying. There are several theories about what this engine could be. One involves the ejector slamming into dense clouds of material that the star shed in its final years before the explosion, converting the kinetic energy of the collision into light. Another involves matter falling back onto the compact remnant at the center. But the theory that has gained perhaps the most traction, the one that elegantly explains both the extreme brightness and the unusual timing, involves something extraordinary hiding at the very heart of the explosion. A magnetar, a rapidly spinning, intensely magnetized neutron star, born in the exact moment of the core's collapse, created by the very death of the star, and carrying, locked inside its furious rotation, a reservoir of energy so enormous that it rivals the energy of the supernova explosion itself. This is a dead star, a stellar corpse, the crushed remnant of a core that can never fuse another atom. And yet, through the remarkable physics of angular momentum and magnetism, it holds the power to make the supernova brighter, longer lasting, and more luminous than anyone thought possible. The star has died, but its remnant is just getting started. We left something behind in that explosion. When we followed the collapse of a massive star's core, we moved past the object at the center almost too quickly. The neutron star, we mentioned it in passing, 12 miles across, unimaginably dense. But then we turned our attention outward, to the shockwave, to the expanding debris, to the light show. We followed the ejector into space and watched them glow from radioactive decay. We let the neutron star sit there in the dark, forgotten, a relic of a dead star with nothing left to contribute. That was a mistake, because that crushed remnant sitting at the center of the explosion is about to become the most important object in this entire story. Let's go back to the moment of collapse and look more carefully this time. When the iron core exceeds the Chandrasekhar limit and electron degeneracy pressure fails, the inner core plunges inward. We covered this, but what we didn't fully appreciate is what emerges from the other side of that collapse. A neutron star is not just a very dense ball of matter. It is one of the most extreme objects in the known universe. Consider what has happened to the matter inside it. In normal matter, atoms are mostly empty space. The nucleus of an atom sits at the center, surrounded by a vast cloud of electrons. If an atom were the size of a football stadium, the nucleus would be a marble sitting at the center of the field. Everything else is empty. The electrons are like gnats buzzing around the outer seats. But in a neutron star, all that empty space has been crushed out. The gravitational pressure is so intense that electrons have been forced into protons, converting them into neutrons. What remains is matter compressed to nuclear density. The atoms are gone. The empty space is gone. What's left is essentially a single enormous atomic nucleus, 12 miles across, containing more mass than our Sun. The numbers that describe a neutron star sound as though they belong in fiction rather than reality. The surface gravity is roughly 200 billion times stronger than Earth's. If you could somehow drop a pebble from a height of 1 meter above the surface, it would reach the ground in about 1 microsecond, accelerating to roughly 4.5 million miles per hour before impact. The surface of a neutron star is not a place anything survives contact with. The gravitational field is so intense that light itself is affected. Photons climbing away from the surface lose energy fighting against gravity, becoming redshifted. The space-time around the neutron star is curved so dramatically that you could actually see the back of the star while looking at its front. Light from the far side bends around the star, follows the curvature of space-time, and reaches your eyes. The entire surface is visible at once, not because the star is transparent, but because space-time itself is warped so severely that light follows curved paths around it. And this object, this 12-mile sphere of compressed nuclear matter, is sitting right at the center of the expanding supernova debris. It was created by the same collapse that triggered the explosion. It is the dead heart of a dead star. But here's what makes a neutron star more than just a gravitational curiosity. It spins. And not gently. Not the way a planet leisurely rotates over the course of a day. A newborn neutron star can spin hundreds of times per second. Some spin so fast that their surfaces move at a significant fraction of the speed of light. And the reason for this furious rotation is one of the most beautiful and intuitive laws in all of physics. Conservation of angular momentum. You've seen this principle in action even if you've never heard the name. Think of a figure skater performing a spin. She starts with her arms extended, rotating slowly, gracefully, in no particular hurry. Then she pulls her arms in close to her body. What happens? She spins faster, much faster. Her rotational speed increases dramatically, seemingly from nowhere. No additional force is applied. No motor kicks in. She simply drew her mass closer to her axis of rotation, and the spin rate increased automatically to compensate. This isn't magic, it's a fundamental conservation law. Angular momentum depends on two things: how fast something is rotating, and how far its mass is distributed from the axis of rotation. The total angular momentum of a system remains constant unless some external force acts on it. So if the radius decreases, if the mass moves closer to the center, the rotation rate must increase to keep the total angular momentum the same. The skater's arms come in, and the spin speeds up. It's the same total angular momentum expressed in a smaller body, which demands a faster spin. Now apply this to a collapsing stellar core. The original star was rotating. Most stars do rotate, though some faster than others. A massive star might complete one full rotation every few weeks, or every few months. That seems slow, and it is slow. The star is enormous. Its radius spans millions of miles. The rotation is lazy, unhurried, barely perceptible. But when the core collapses, everything changes. The core shrinks from roughly the size of Earth, about 8,000 miles across, down to a sphere about 12 miles across. That is a reduction in radius by a factor of roughly 1,000. And conservation of angular momentum doesn't care that the star has just undergone the most violent event of its existence. The law holds. The math is simple and merciless. If the radius decreases by a factor of 1,000, the spin rate increases by a factor of roughly 1,000,000. A core that was completing one rotation every several hours suddenly becomes a neutron star, completing hundreds of rotations every single second. The collapse takes less than 1 second. In that fraction of a second, a lazy, slow-spinning core becomes one of the fastest rotating objects in the known universe. Think about that transformation. Picture a carousel that completes one rotation every 30 seconds, and then imagine compressing it to the size of a coin. Conservation of angular momentum would spin that coin so fast, it would be nothing but a blur. Now, imagine doing that to something with more mass than the Sun. The energy locked inside that rotation is extraordinary. We can actually observe this directly. Neutron stars that emit beams of radiation from their magnetic poles are called pulsars, because as they spin, the beam sweeps across our line of sight like a lighthouse, and we detect a regular pulse of radiation with each rotation. By measuring the interval between pulses, astronomers can determine exactly how fast the neutron star is spinning. The Crab pulsar, the neutron star at the center of the Crab Nebula, the remnant of that supernova recorded by Chinese astronomers in 1054, rotates about 30 times per second, and the Crab Nebula is nearly 1,000 years old. The pulsar has been gradually losing rotational energy over all that time. When it was first born, it was spinning much faster. The fastest known pulsars, called millisecond pulsars, can spin at over 700 rotations per second. 700 full revolutions in a single second. The surface of such a pulsar, even though the star is only about 12 miles across, is moving at roughly 15% of the speed of light. At that rate, a point on the equator of the neutron star completes a full trip around the entire circumference in less than 1.5 milliseconds. The rotation is so fast that the star becomes noticeably flattened at the poles, bulging slightly at the equator from the centrifugal effect, even though the object is made of the densest material in the universe, short of a black hole. These rotation rates are real. They are measured. They are confirmed by decades of pulsar observations spanning the electromagnetic spectrum. Some pulsars keep time so precisely that they rival atomic clocks. Neutron stars are among the most accurately timed natural objects in existence. Now here's where things become truly remarkable. A rapidly rotating neutron star doesn't just spin passively. That rotation represents an enormous reservoir of stored energy. Rotational kinetic energy. The same kind of energy stored in any spinning object, from a top on a table to a flywheel in a machine. But the amount of energy stored in a spinning neutron star is on an entirely different scale from anything in everyday experience. How much energy are we talking about? Rotational kinetic energy depends on two things: how massive and how wide the spinning object is, which determines something called its moment of inertia, and how fast it's rotating. A neutron star has a modest radius of only about 12 miles, but it has enormous mass, 1.5 to 2 times the mass of our Sun, and it's spinning hundreds of times per second. When you put these together, the total rotational kinetic energy stored in a neutron star spinning at a period of just a few milliseconds turns out to be staggering. To put it in the most useful context, compare it to the supernova itself. The total kinetic energy of the expanding supernova debris, all that material flying outward through space at 10,000 miles per second, is enormous. But a rapidly spinning magnetar can hold roughly 10 times more energy in its rotation alone than the entire expanding debris cloud carries in its motion. 10 times more. The dead remnant at the center holds more energy in its spin than the whole violent event that created it carries in the outward rush of its debris. This is an almost absurd situation. Imagine setting off a bomb and then discovering that a tiny fragment at the center of the blast contains 10 times more energy than the bomb itself released. A hidden battery, wound tight by the very forces that triggered the detonation, sitting quietly in the wreckage, waiting to unleash its power. Let me try to make you feel this number, because I've said it quickly and I think it deserves more weight. The magnetar holds roughly 10 times more energy in its rotation than the entire expanding supernova carries in its outward motion. But what does that actually mean in terms you can connect to something real? Let's start with the sun. Our sun produces an extraordinary amount of energy. Every single second, the sun releases roughly 400 trillion watts. That's enough energy in 1 second to power all of human civilization for hundreds of thousands of years. The sun has been doing this for 4.5 billion years and will continue for another 5 billion. The total energy the sun will radiate over its entire 10 billion year main sequence lifetime is staggering. It's an amount of energy so large that we normally only encounter it in astrophysics textbooks. A rapidly spinning magnetar holds more rotational energy than the sun will radiate over its entire 10 billion year lifetime. Not a year of solar output. Not a million years. The sun's total energy budget from birth to death multiplied roughly 20 times over, all of it stored in the spin of a single object 12 miles across. If you could somehow hook a generator to a newborn magnetar, it could replace the sun for its entire natural life and still have energy left over. Or think about it from a human energy perspective. All the electricity generated by every power plant on Earth in an entire year adds up to a tiny fraction of 1% of the sun's output. The magnetar's rotational energy exceeds humanity's total annual energy consumption by a factor so large that writing out the number would fill a line on this page with zeros and still communicate nothing meaningful to your intuition. It's not that the number is merely big, it's that it exists in a category your brain has no container for. And all of this energy is stored in rotation. Not in chemical bonds, not in nuclear fuel, in the spinning of mass. The same type of energy that exists in a child's toy top or a potter's wheel, just scaled up by a factor that makes the comparison almost comical. A spinning top on a table stores a tiny amount of rotational energy. If you scaled that top up to the mass of the sun and spun it hundreds of times per second, you would be approaching, in the loosest possible sense, what a magnetar carries. The physics is identical. The scale is not. What makes this even more extraordinary is that this energy wasn't added from outside. Nobody wound the magnetar up. No external force spun it to these speeds. The rotation is a direct, unavoidable consequence of the collapse itself. The star's core was rotating slowly before it fell. The collapse compressed it. Conservation of angular momentum did the rest. The energy was always there, spread across a slowly rotating core the size of a planet. The collapse simply concentrated it, squeezed it down into a 12-mile sphere, and in doing so, transformed a modest amount of rotational energy into a colossal one. It's as though you took a gently flowing river, a broad, lazy current spreading across a wide floodplain, and suddenly funneled it through a pipe a few inches wide. The same volume of water that drifted peacefully across a mile-wide riverbed would now blast through that pipe at ferocious speed. The water wasn't added. The energy wasn't created. It was concentrated. focused, compressed into a form so intense that it becomes something qualitatively different from what it was before. That is what collapse does to angular momentum. It takes the gentle spin of a massive core and compresses it into a furious, screaming rotation that contains more energy than the explosion that triggered it. And none of this energy is locked away permanently. It's not sealed inside the spin with no way out. The magnetar has a mechanism for releasing its rotational energy, converting it into outgoing power, and we're about to explore that mechanism in detail. But to truly appreciate why it changes everything, why it transforms our understanding of how bright a supernova can become, we need to understand one more thing about the energy budget. Because the comparison between the magnetar's reservoir and the visible output of a normal supernova is where this story stops being merely interesting and starts being extraordinary. And the comparison gets even more dramatic. The amount of energy radiated as visible light by a typical core collapse supernova, the actual luminosity we observe through our telescopes, is roughly 1% of the explosion's kinetic energy. So the magnetar's rotational energy can exceed the total visible light output of a normal supernova by a factor of 1,000. 1,000 times more energy than the supernova shines with invisible light, all of it locked inside the spin of a 12-mile sphere of nuclear matter. If even a small fraction of that rotational energy could be tapped, if even a few percent of it could be converted into visible radiation, the supernova would appear dramatically, overwhelmingly brighter than any normal core collapse supernova could ever be. And that is exactly what seems to happen. But before the magnetar can act as an engine, we need to understand what makes it a magnetar in the first place. Because not all neutron stars are magnetars. Most neutron stars have strong magnetic fields, but magnetars are in a class entirely their own. An ordinary neutron star has a magnetic field about 1 trillion times stronger than Earth's. That already sounds extreme, and it is. Earth's magnetic field is what makes compass needles point north. It shields our atmosphere from the solar wind. And an ordinary neutron star's field is 1 trillion times more powerful than that. But a magnetar's field is 1,000 times stronger still. A magnetar possesses a magnetic field roughly 1 quadrillion times stronger than Earth's. 1 quadrillion. That's a 1 followed by 15 zeros. This makes magnetars the most powerfully magnetized objects known to exist anywhere in the universe. Let me try to help you feel how strong this is. A typical refrigerator magnet produces a field of about 50 Gauss. Gauss is a unit used to measure magnetic field strength. Earth's magnetic field at the surface is about half a Gauss. An MRI machine at a hospital, the kind that creates detailed images of your internal organs using powerful magnets, operates at roughly 30,000 Gauss. That's strong enough that all metal objects must be removed before anyone enters the room. Strong enough that the magnetic force can yank a metal chair across the floor and slam it into the machine if someone is careless. An ordinary neutron star's magnetic field is on the order of 1 trillion Gauss. That's already about 30 million times stronger than an MRI machine. At that field strength, atoms are physically distorted. The electron clouds around atomic nuclei, normally roughly spherical, are stretched and compressed into long, thin cylinders aligned with the magnetic field. Chemistry, as we know it, cannot function. Molecules cannot hold their normal shapes. A magnetar takes this to another level entirely. At 1 quadrillion Gauss, the the magnetic field begins to affect the very fabric of empty space. The vacuum itself becomes birefringent, meaning light traveling through it splits into two differently polarized beams, the way light splits when passing through certain crystals. The field is strong enough to tear atoms into unrecognizable configurations, destroying normal electron orbits entirely. Matter near a magnetar doesn't behave like any matter you've ever encountered. The magnetic field dominates everything, overriding the electromagnetic forces that give matter its ordinary structure. How do magnetars develop such extreme fields? This remains an active area of research, but the leading theory involves what happens during the first few seconds of the neutron star's existence. In the first 10 to 30 seconds after formation, the interior of the neutron star is not yet settled. It's a turbulent, violently churning sea of ultra-dense matter, incredibly hot, roiling with convective currents. Picture boiling water, but instead of water molecules, the fluid is made of neutrons, and instead of a pot on a stove, the container is the gravitational field of a stellar corpse. In these conditions, a dynamo can operate. The same kind of process that generates magnetic fields inside Earth and the Sun, but dramatically amplified by the extreme circumstances. Convective currents of electrically conducting fluid, moving rapidly through existing magnetic field lines, stretch and amplify those field lines. The turbulence winds the field tighter and tighter, boosting its strength by orders of magnitude. Within seconds, the magnetic field can be amplified from the already powerful levels of an ordinary neutron star up to the almost incomprehensible levels of a magnetar. The speed of the neutron star's initial rotation plays a crucial role here. A faster spinning neutron star drives more vigorous convection, which produces a stronger dynamo, which creates a more powerful magnetic field. This establishes a fascinating relationship. The very thing that stores the energy, the rapid rotation, is also the thing that helps create the mechanism for releasing it. The ultra-strong magnetic field. The engine builds itself. Not every collapsing core produces a magnetar. If the core isn't spinning fast enough, if the conditions aren't quite right during those first critical seconds, the neutron star forms with a strong but not extraordinary magnetic field. It becomes an ordinary pulsar, interesting in its own right, but lacking the extreme magnetism needed to act as the kind of engine we're interested in. Magnetars are probably rare, perhaps 1 in 10 neutron stars, maybe fewer. But when they do form, they become some of the most powerful objects in the known universe. And we know magnetars are real because we've observed their effects directly. Even isolated magnetars, those not hidden inside fresh supernova debris, reveal themselves through spectacular outbursts of energy. In late 2004, a magnetar designated SGR 1806-20, located roughly 50,000 light-years away near the center of our own galaxy, released a burst of energy so powerful that it briefly outshone every other X-ray source in the sky combined. The burst lasted only about 1/10 of a second at its peak, but during that fraction of a second, the magnetar released more energy than our sun produces in roughly 250,000 years. The flash was so intense that it measurably affected Earth's upper atmosphere, ionizing gas in the ionosphere from 50,000 light-years away. A dead star, halfway across the galaxy, physically altered the chemistry of our planet's atmosphere for a brief moment. And that was just a single surface burst, caused by a sudden rearrangement of the magnetar's ultra-strong magnetic field, something like a magnetic earthquake, fracturing the neutron star's rigid crust. The energy available from the magnetar's full rotation, the deeper reservoir we've been discussing, is millions of times greater than what was released in that one outburst. Imagine what happens when that full rotational reservoir is tapped steadily over the course of weeks or months. Not in a sudden flash, but in a continuous, sustained flow. That is the engine we've been looking for. So how does the magnetar actually convert its stored rotational energy into outgoing power? Through a process called spin down. The magnetar is spinning rapidly, and it carries that extraordinarily powerful magnetic field anchored in its crust and interior. As the magnetar rotates, the magnetic field rotates with it, sweeping through space like the beam of a lighthouse. But this beam isn't ordinary light. It's an intense, rapidly changing electromagnetic field extending outward from the neutron star in all directions. This rotating magnetic field does two critical things. First, it radiates energy directly. A rotating magnetic dipole, which is what a spinning magnetized neutron star approximates, emits electromagnetic radiation simply by virtue of its rotation. This is called magnetic dipole radiation. The power emitted depends very strongly on both the strength of the magnetic field and the speed of the rotation. For an ordinary pulsar with a relatively modest field, this radiation is significant but manageable. For a magnetar with a field 1,000 times stronger, the power output is extraordinary. The radiated power scales as the square of the magnetic field strength. A 1,000-fold increase in field strength means a 1,000,000-fold increase in radiated power. A magnetar bleeds its rotational energy away millions of times faster than an ordinary pulsar would. Second, the magnetic field accelerates charged particles. Any electron, positron, or ion near the magnetar's surface feels the enormous force of the rotating magnetic field. The field lines extend outward from the neutron star's magnetic poles, and as they sweep around, they accelerate particles to immense energies. These particles are flung outward along the field lines, spiraling, radiating as they go, producing what physicists call a magnetar wind. This magnetar wind is a relentless flood of energetic particles and high-energy radiation streaming outward from the neutron star in all directions. Think of it as a continuous, powerful gale blowing away from the magnetar, carrying with it the rotational energy of the spinning neutron star, steadily converting the spin of a dead stellar core into an outgoing river of power. The result of this process is that the magnetar steadily loses rotational energy. It slows down. Every wave of radiation it emits, every particle it flings outward, carries away a portion of its spin. The magnetar is decelerating, spinning down, converting its vast reservoir of rotational kinetic energy into outflowing power that races outward from its surface. And the rate at which this happens is set primarily by the strength of the magnetic field. A stronger field means faster spin down. Faster spin down means the rotational energy is released more quickly, in a more concentrated burst of power over a shorter time span. For the magnetar field strengths we're considering, the spin down timescale turns out to be days to months. This is a crucial detail. The magnetar releases most of its rotational energy over a period that matches almost perfectly with the timescale over which superluminous supernovae remain bright. Not milliseconds, not millennia, days to months. The same window of time during which astronomers observe these extraordinarily luminous explosions sustaining their brightness against all expectations. This match in timescales is not a coincidence. It's one of the strongest arguments in favor of the magnetar engine model. If the magnetar's energy were released in a fraction of a second, it wouldn't help explain sustained luminosity over weeks and months. If it were released over thousands of years, it would produce only a faint, barely noticeable boost spread too thin to matter. But the spin-down timescale of a strongly magnetized, rapidly rotating neutron star naturally falls in exactly the right range to power a super luminous supernova. The physics produces the right answer without being forced. Without fine-tuning, without ad hoc adjustments, the mechanism simply works. Let me walk you through the picture we have assembled, because we've built something remarkable here. A massive star reaches the end of its nuclear fuel. Its iron core collapses. The outer layers are blasted outward in a core collapse supernova. In the heart of the explosion, the collapsing core is crushed into a neutron star. Conservation of angular momentum spins it up to hundreds of rotations per second. A convective dynamo operating in the first critical seconds of the neutron star's existence amplifies its magnetic field to magnetar levels, a quadrillion times stronger than Earth's. The result is a rapidly rotating, intensely magnetized neutron star sitting at the center of an expanding cloud of debris. This magnetar holds in its rotation a reservoir of energy 10 times greater than the kinetic energy carried by all the expanding material around it. Through magnetic braking, through the physics of a spinning magnetic dipole, the magnetar steadily converts that rotational energy into an intense wind of accelerated particles and high-energy radiation. It pours energy outward into the surrounding debris over a timescale of days to months. The star is dead. Its core will never fuse another atom. By every traditional measure, it has nothing left to give. And yet the remnant it left behind, the crushed, spinning, magnetized corpse at its center, carries more energy than the explosion itself, and is now actively releasing that energy into the expanding wreckage. This is the engine. This is the hidden power source that can explain how a supernova shines 10 or 50 or 100 times brighter than radioactive decay alone could ever produce. The dead star is pumping energy back into its own explosion. But having an engine is only half the story. What matters is what happens when that energy actually enters the expanding debris. Because the magnetar wind doesn't simply pass through the ejector and escape into open space. The ejector are dense, they're opaque. They form a thick, expanding shell of hot gas surrounding the magnetar on all sides, a wall of material through which the high-energy radiation and particles must fight their way out. And this interaction between the magnetar's energy output and the surrounding ejector is where the real transformation occurs. This is where high-energy radiation invisible to our telescopes gets converted into the visible light that makes these supernovae shine so spectacularly. This is where a hidden engine becomes a visible phenomenon. This is the mechanism that takes stored rotational energy and turns it into the brightest stellar explosions in the universe. Because the ejector don't just sit there passively. They absorb the magnetar's energy. They trap it. They process it. They transform it. And they re-radiate it in a completely different form, at completely different wavelengths. The harsh, high-energy output of a spinning magnetar goes in, and soft, warm, visible light comes out the other side. The ejector are not just debris, they are a converter. A machine that takes the raw power of a dead star's rotation and repackages it into the most luminous light show the universe has to offer. And the way that conversion works, the detailed physics of trapping and reprocessing and re-emission, and the way it changes over time as the ejecta expand and thin and eventually become transparent, revealing the engine within, that is where our story goes next. We now have our engine. A rapidly spinning magnetar, born in the collapse, holding a vast reservoir of rotational energy, steadily releasing that energy through spin down into an outgoing flood of accelerated particles and high energy radiation. The engine is running, the power is flowing. But here's the problem. If that energy simply poured outward through the expanding ejecta and escaped directly into space, we wouldn't see a super luminous supernova. We would see an extraordinarily powerful source of gamma rays and X-rays, a brilliant beacon visible only to specialized space telescopes designed to detect the most energetic forms of light. Your eyes wouldn't register it. Optical telescopes wouldn't detect it. The energy would be there, but it would be invisible at the wavelengths that astronomers use to measure supernova brightness. The reason superluminous supernovae are so remarkable isn't just that they contain enormous amounts of energy, it's that they radiate that energy as visible light, as the kind of light your eyes can actually see, as the wavelengths that make a supernova look spectacularly, impossibly bright when viewed through optical telescopes. And that transformation from invisible high-energy radiation to visible light doesn't happen automatically. It requires something between the magnetar and the observer. Something that can absorb the ferocious output of the magnetar engine and reprocess it, convert it, translate it into a gentler form. That something is the ejecta, the expanding debris of the destroyed star, the same material that was blasted outward by the initial explosion. And it turns out the ejecta don't just passively surround the magnetar, they actively participate in the process. They are the crucial intermediary, the converter, the machine that takes the raw, high-energy output of a spinning dead star and transforms it into the most luminous optical display the universe can produce. Let's understand how. In the first days and weeks after the explosion, the ejecta are dense, extraordinarily dense. Remember, the outer layers of a massive star have just been violently ejected, and they haven't had much time to spread out. The material is expanding at thousands of miles per second, but there's a lot of it. Several times the mass of our sun in some cases, all compressed into a relatively small volume that's only just beginning to inflate. The ejecta form a thick, opaque shell surrounding the central magnetar, a cocoon of hot gas through which very little radiation can pass. Opacity is the key concept here. Opacity measures how effectively a material blocks the passage of light. A material with high opacity is like a thick fog. Photons, particles of light, cannot travel far before they're absorbed or scattered by the particles of the material. They collide with the electrons and atoms, lose their original direction, get absorbed, and are re-emitted in random directions. Each photon takes a tortuous, zigzagging path through the material, bouncing from interaction to interaction, never traveling in a straight line for long. The newly formed supernova ejecta have extremely high opacity at early times. The gas is hot enough that many of its atoms are ionized, stripped of their electrons. Those free electrons are extraordinarily efficient at interacting with photons, especially high-energy photons like gamma rays and X-rays. A gamma ray photon entering this dense ionized gas doesn't sail through cleanly. It slams into a free electron almost immediately. The collision is called Compton scattering, and it does something very specific and very important. The photon transfers some of its energy to the electron. The photon comes out of the collision with less energy than it went in with, and the electron flies off with the difference. The photon has been degraded. It started as a gamma ray, and it's now a slightly less energetic gamma ray, or perhaps an X-ray. The photon has taken a step down the energy ladder, but one step isn't enough. The photon is still highly energetic, so it continues through the gas and almost immediately hits another electron. Another Compton scattering event. Another transfer of energy. Another step down the ladder. The photon loses more energy, dropping further, from hard X-ray to soft X-ray. Then another collision. Soft X-ray to extreme ultraviolet. Another collision. Extreme ultraviolet to ultraviolet. Then to violet visible light. Then to blue. Then to green. Then to yellow. Then to red. Each collision steals a little more energy from the photon, stretching its wavelength, pushing it toward the lower energy end of the electromagnetic spectrum. This process is called thermalization. The high energy radiation emitted by the magnetar is being thermalized, converted into thermal radiation that matches the temperature of the surrounding gas. It's like pouring boiling water into a bathtub full of cool water. The hot water doesn't stay hot. It mixes with the cooler water, sharing its energy, until everything reaches an intermediate temperature. The extreme heat of the boiling water has been spread out, diluted, absorbed by the larger volume of cooler water. The result is warm water. Not scalding, not freezing. Warm. Similarly, the extreme energy of the magnetar's gamma rays is spread out, diluted, absorbed by the vast mass of the ejector. The result is radiation at a much lower energy. Warm light. Visible light. But it's not just Compton scattering that does this work. The ejector contain heavy elements. Atoms of iron, nickel, cobalt, silicon, oxygen, and dozens of other elements forged in the star's core and scattered through the debris by the explosion. These atoms, and especially their ions, have complex electron structures with many possible energy levels. When a photon of the right energy encounters one of these ions, it can be absorbed entirely. The ion swallows the photon, and one of its electrons jumps to a higher energy state. A moment later, the electron drops back down, but it doesn't necessarily emit a single photon at the same energy it absorbed. Instead, it might drop down through multiple intermediate energy levels, releasing 2 or 3 or 4 lower energy photons instead of one high energy one. A single ultraviolet photon goes in, and several visible light photons come out. This process, called line absorption followed by fluorescent re-emission, is another powerful mechanism for converting high energy radiation into lower energy visible light. Together, Compton scattering and line absorption work in concert to take the fierce, high energy output of the magnetar and grind it down into softer, lower energy radiation that emerges from the ejector as visible and ultraviolet light. The ejector acts as a filter, a converter, a downshifting machine. They take in gamma rays and X-rays that human eyes can't see, and they produce the brilliant visible glow that makes a superluminous supernova so spectacular. There's a beautiful analogy for what's happening here. Think of a greenhouse. Sunlight passes through the glass walls of a greenhouse as visible light. The plants and soil inside absorb that sunlight and re-radiate the energy as infrared radiation, as heat. But infrared radiation can't pass back through the glass as easily as visible light can. It's trapped. The greenhouse heats up because energy can get in more easily than it can get out. The ejector surrounding the magnetar work on a similar principle, but in reverse. High energy radiation from the magnetar is absorbed by the dense ejector. It can't escape in its original high energy form because the ejector are opaque to gamma rays and X-rays. The energy is absorbed, reprocessed, and re-radiated at lower energies, visible and ultraviolet wavelengths, where the ejector are somewhat more transparent. Energy enters as hard radiation that can't escape. It leaves a softer radiation that can. The result is that the ejector become a glowing lantern. They're heated from within by the magnetar's continuous energy input, and they radiate that thermal energy outward as visible light. The ejector have a photosphere, an outer surface from which light escapes, just as the sun has a visible surface from which sunlight escapes. The temperature of this photosphere determines the color and spectrum of the emitted light. In the weeks after the explosion, when the magnetar is pumping in energy at its highest rate, the photosphere can reach temperatures of 10,000 to 20,000 degrees or more. At these temperatures, the ejector glow blue-white, radiating strongly in the ultraviolet and blue portions of the spectrum. As time passes and the magnetar's energy output gradually diminishes as it spins down, the photosphere cools, and the light shifts toward cooler colors. Blue-white becomes white, white becomes yellow. Yellow eventually becomes orange and red as the ejector cool further. Now, here's why the magnetar model produces such spectacular brightness. In an ordinary core collapse supernova, the only energy source available after the initial explosion is radioactive decay. Nickel-56 decays into cobalt-56, which decays into iron-56. Each decay releases a fixed amount of energy. And once the nickel-56 is formed, that's it. There's no way to add more. The total energy budget is set at the moment of the explosion, and from that point forward, the energy can only decrease as the radioactive material is consumed. The light curve is a one-way street. The supernova brightens, peaks, and then declines steadily as the radioactive fuel runs out. But with a magnetar engine, the situation is fundamentally different. The magnetar is continuously injecting fresh energy into the ejector. Energy that doesn't come from radioactive decay. Energy that comes from the rotational reservoir of the neutron star. And this reservoir is enormous, far larger than what any reasonable quantity of nickel-56 could provide. So the ejector are receiving far more energy than they would from radioactive decay alone. And they're receiving it continuously over weeks and months as the magnetar steadily spins down. This does two things simultaneously. It makes the supernova brighter at its peak, because the total energy being pumped into the ejector at any given moment is much greater than radioactive decay alone could supply. And it makes the supernova stay brighter for longer, because the magnetar continues injecting energy well after the radioactive decay would have diminished to negligible levels. The light curve doesn't follow the cobalt-56 decline. It stays elevated. It can plateau for weeks. It can decline more slowly than radioactive decay permits. The magnetar is holding the supernova up, sustaining its brilliance against the natural tendency to fade. Think about it this way. Imagine two campfires. One is an ordinary fire. You light the logs, they burn, the fire blazes, and then it slowly dies down as the fuel is consumed. That's a normal supernova. The radioactive fuel burns and the light fades, Now imagine a second campfire with a hidden electric heater buried under the logs. Even as the logs burn down, the heater keeps pouring heat into the fire pit. The campfire stays hot. It stays bright. Long after the logs should have turned to cold ash, the fire continues glowing because of the hidden energy source underneath. That's a magnetar-powered supernova. The hidden heater is the magnetar. The logs are the ejector. The visible glow is the light that reaches our telescopes. But there's an important detail we need to address. This whole mechanism works because the ejector are dense enough to trap the magnetar's energy and reprocess it into visible light. What happens as time passes and the ejector continue expanding? The ejector are moving outward at thousands of miles per second. Every day, the expanding shell grows larger, and as it expands, it thins out. The same mass of material occupies a larger and larger volume. This means the density drops. The opacity decreases. The material that was initially thick and opaque, capable of trapping gamma rays and X-rays completely, gradually becomes more transparent. This transition from opaque to transparent happens gradually, and it creates a remarkable observational signature. In the early weeks, when the ejector are still dense, essentially all the magnetar's energy is trapped and thermalized. Very little high-energy radiation escapes. The supernova is brilliantly luminous in visible light, but nearly invisible in gamma rays. The energy conversion is almost complete. Nearly everything goes in as gamma rays and comes out as optical light. But as weeks turn into months and the ejector thin out, cracks begin to appear in the cocoon. Not literal cracks, but regions where the opacity has dropped enough that higher energy photons can begin to slip through. First, the softest X-rays find pathways out. Then harder X-rays. And eventually, as the ejector becomes sufficiently transparent, even gamma-ray photons can escape without being fully thermalized. This is gamma-ray leakage, and it is one of the most important diagnostic tools astronomers have for detecting a magnetar engine inside a supernova. Here's why. If a supernova is powered only by radioactive decay, the gamma rays it produces come from a known source, the decay of cobalt-56. These gamma rays have specific energies, specific spectral signatures that identify them as products of radioactive decay. Astronomers know exactly what to look for. But if a magnetar engine is operating inside the ejector, the situation changes. The magnetar produces its own population of high-energy photons, with a different energy distribution, a different spectral character, a different time evolution than radioactive decay would produce. As the ejector thin out and gamma rays begin to leak through, those escaping photons carry information about what's happening inside. They're messengers from the hidden engine. The timing of gamma ray leakage also matters enormously. Radioactive decay-powered gamma rays should appear on a predictable schedule, following the cobalt-56 decay curve, declining steadily with the 77-day half-life. But if a magnetar is the power source, the gamma ray signal can behave differently. It can appear later than expected, because the magnetar's energy input keeps the ejector hot and ionized for longer, maintaining high opacity later into the supernova's evolution. Or the gamma ray flux can be higher than radioactive decay alone would predict. Because the magnetar is producing more high-energy radiation than any reasonable quantity of cobalt-56 could generate. In either case, detecting gamma rays from a super-luminous supernova and carefully analyzing their energy, their timing, and their intensity gives astronomers a way to peer behind the curtain. It lets them look past the brilliant visible light display and see the engine that's driving it. It turns a beautiful but mysterious light show into a diagnostic puzzle with specific, testable predictions. The transition from opaque to transparent also affects the visible light output. As the ejecta thin out and become less effective at trapping energy, more and more of the magnetar's output leaks through without being fully converted to visible light. The conversion efficiency drops. Less energy is reprocessed into optical wavelengths. The supernova begins to fade in visible light, not because the magnetar has stopped producing energy, but because the ejecta can no longer trap and convert it as effectively. Eventually, the ejecta become essentially transparent. The magnetar wind and its associated radiation pass through the thinned out debris almost without interaction. At that point, the supernova's visible light display is essentially over. The ejecta are no longer glowing with reprocessed magnetar energy. They're just expanding, cooling, fading into the interstellar medium. The magnetar itself might still be spinning, still emitting radiation, but without the dense ejecta to act as a converter, that radiation no longer produces a spectacular visible light display. The show ends not because the engine dies, but because the converter runs out. The lantern's walls become transparent, and the light inside has nothing left to catch it. Let me walk you through the complete chain of events one more time, from beginning to end, because the full mechanism is breathtaking in its elegance, and each link connects to the next with remarkable precision. A massive star exhausts its nuclear fuel. Its iron core, inert and lifeless, collapses under its own gravity. In less than a second, the core is crushed from the size of Earth to a sphere 12 miles across, forming a neutron star. Conservation of angular momentum spins this neutron star up to hundreds of rotations per second. In the first few turbulent seconds of the neutron star's existence, a convective dynamo amplifies its magnetic field to magnetar levels, a quadrillion times stronger than Earth's magnetic field. The magnetar now holds in its rotation a reservoir of energy that rivals or exceeds the kinetic energy of the entire supernova explosion. Through magnetic braking, the rapidly rotating magnetic field radiates energy and accelerates charged particles, producing a powerful magnetar wind. This wind carries the rotational energy outward from the neutron star's surface, but the magnetar is not sitting in empty space. It's surrounded on all sides by dense, opaque supernova ejecta, the shattered outer layers of the dead star, expanding outward but still thick enough to trap nearly all incoming high-energy radiation. The magnetar wind slams into this wall of debris. The ejecta absorb the magnetar's energy. Through Compton scattering, free electrons in the ionized gas collide with high-energy photons, stealing their energy step by step, degrading gamma rays into X-rays, into ultraviolet, into visible light. Through line absorption and fluorescent re-emission, heavy element ions swallow individual photons and re-emit multiple lower energy photons. The fierce, invisible, high energy output of the magnetar is ground down, softened, reprocessed into thermal radiation at visible wavelengths. The ejecta glow. They become a brilliant photosphere, heated from within by the continuous energy input of the spinning magnetar. The supernova shines in visible light, far brighter than radioactive decay alone could ever produce, because the energy source powering the display is not a finite supply of unstable isotopes, but the colossal rotational energy of a magnetar, which dwarfs the radioactive energy budget by orders of magnitude. The magnetar continues to spin down over days and weeks and months. its energy output gradually diminishes as it loses rotational speed. But for an extended period, it pours enough energy into the ejector to keep the supernova shining at extraordinary luminosities, sustaining a brightness that defies the predictions of the radioactive decay model. As the ejector expand and thin out over months, their opacity decreases. Higher energy photons begin to leak through without being fully thermalized. Gamma rays escape. These escaping gamma rays carry the fingerprint of the magnetar engine, their energies and timing distinct from what radioactive decay alone would produce. Gamma ray telescopes orbiting above Earth's atmosphere can detect these photons and use them to diagnose what's happening inside the supernova, confirming or constraining the presence of a magnetar engine. Eventually, the ejector becomes transparent. The conversion of magnetar energy into visible light ceases. The supernova fades from view in optical light, but the magnetar remains, spinning more slowly now, its energy substantially spent, a dead star at the center of an expanding ghost of debris. A stellar corpse that for weeks or months defied the darkness by pouring its hidden reserves into the explosion that created it. This entire sequence, from collapse to magnetar formation to spin down to energy injection to trapping to thermalization to visible light emission to gamma ray leakage, this is the magnetar engine model. It is one of the leading explanations for the extraordinary luminosities of superluminous supernovae, and every step in the chain is grounded in well-understood physics: conservation of angular momentum, electrodynamics of rotating magnetic dipoles, Compton scattering, radiative transfer through dense media. Each piece has been tested independently in other astrophysical contexts. What the magnetar engine model does is assemble these pieces into a coherent narrative that explains how a dead star can make its own supernova brighter. And there's something deeply poetic about this mechanism. The star dies. Its core collapses into a remnant that, by every conventional measure, is a corpse. It will never fuse another atom. It will never generate nuclear energy again. But the physics of angular momentum and magnetism conspire to give this corpse one final gift: a vast reservoir of rotational energy that it can pour back into the explosion that created it. The dead star doesn't just passively sit at the center of the expanding debris. It actively participates. It pushes energy outward into the ejector. It sustains the supernova's brilliance. It holds the light up against the natural tendency to fade. In a real sense, the death of the star doesn't end the story. It starts a new chapter. A chapter in which the remnant becomes more important than the original explosion. A chapter in which the corpse outshines the funeral. We've now built the complete theoretical framework, the engine, the energy reservoir, the mechanism of energy transfer, the process of thermalization, the visible light display, the diagnostic signature of gamma ray leakage. Everything fits together into a coherent physical picture that can be tested against observations. And that is exactly what astronomers have done. Because in 2017, a supernova appeared that would put this model to one of its most important tests yet. A supernova that was bright where it shouldn't have been, in a galaxy that didn't fit the usual pattern, observed across multiple wavelengths over months and years. A supernova that, nearly a decade later, would reveal something hidden inside it, evidence of the very engine we've spent this entire journey describing. That supernova has a name, and it has a story that brings everything we've discussed from theory into the realm of observational reality. In late May of 2017, a robotic survey telescope scanning the sky for transient events flagged something new. A point of light that hadn't been there before, brightening rapidly in a galaxy roughly 420 million light-years from Earth. Astronomers turned their attention to it quickly, because the initial readings suggested this wasn't an ordinary supernova. The brightness was climbing too fast, reaching luminosities far beyond what a typical core collapse event should produce. Within days, spectroscopic observations confirmed what the light curve was already screaming. This was a super luminous supernova. One of those impossibly bright explosions that defies the predictions of radioactive decay models. It was designated SN 2017 EGM, and it was about to become one of the most carefully studied stellar explosions in history. But here's the first thing that made this supernova unusual, and it had nothing to do with the explosion itself. It was the galaxy it appeared in. Before 2017, superluminous supernovae had been found almost exclusively in small, faint, metal-poor dwarf galaxies. This was a strong and consistent pattern. Astronomers had catalogued dozens of superluminous supernovae by that point, and the overwhelming majority occurred in galaxies that were dim, compact, and chemically primitive. These dwarf galaxies contained relatively few heavy elements heavier than hydrogen and helium that astronomers call metals. The connection seemed meaningful. Perhaps the conditions needed to produce a superluminous supernova. Whether those conditions involved the magnetar model or some other mechanism, required a low metallicity environment. Perhaps stars in metal-poor galaxies evolved differently, retained more angular momentum in their cores, or lost less mass through stellar winds, making them more likely to produce the kind of rapidly spinning, highly magnetized neutron star that could power an extreme explosion. This made intuitive sense. Stars rich in heavy elements tend to have stronger stellar winds, because metals in their outer layers absorb more radiation, which drives material outward into space. A star that loses more mass through winds arrives at core collapse lighter and slower spinning than it would have been otherwise. A metal-poor star, by contrast, holds onto its mass more effectively. It arrives at collapse heavier and potentially faster spinning. Faster spin in the core means more rotational energy in the resulting neutron star, which means a more powerful magnetar engine. The connection between low metallicity and superluminous supernovae fit neatly into the magnetar model. And then SN 2017 EGM broke the pattern. Its host galaxy, designated NGC 3191, is not a faint dwarf galaxy. It's a large, massive, metal-rich spiral galaxy. A galaxy much more similar to our own Milky Way than to the tiny, chemically primitive dwarfs where superluminous supernovae had been found before. NGC 3191 contains roughly as many stars as the Milky Way. It has a well-developed spiral structure. Its chemical composition is rich in heavy elements. By every metric that astronomers had been using to predict where superluminous supernovae should occur, this galaxy was wrong. This immediately told astronomers something important. Whatever mechanism produces superluminous supernovae, it isn't restricted to metal-poor environments. It can happen in large, chemically enriched galaxies too. The earlier pattern, the strong preference for dwarf galaxies, might have been partly a selection effect. Superluminous supernovae in dwarf galaxies are easier to spot because the host galaxy is faint, so the supernova stands out dramatically against the dim background. In a large, bright galaxy like NGC 3191, a superluminous supernova has to compete with the combined light of hundreds of billions of stars. It's harder to notice, harder to identify. Some may have been missed in earlier surveys simply because they were hidden in the glare of their host galaxies. SN 2017 EGM was found precisely because survey telescopes were getting better, scanning larger areas more frequently with greater sensitivity. It was a reminder that the universe doesn't always fit neatly into the categories we construct. Nature is messier than our models. The supernova itself was spectacular. At peak brightness, it outshone its entire host galaxy. A single dying star, for a brief window of time, radiating more visible light than all the hundreds of billions of stars in NGC 3191 combined. The peak luminosity was roughly 30 billion times the luminosity of our sun. That's extraordinary. Even for a superluminous supernova, it was remarkable. The light curve rose steeply, peaked, and then declined. But the decline was slower than the cobalt-56 decay rate would predict. The supernova stayed bright longer than it should have if radioactive decay were the only energy source. Astronomers around the world mobilized. Observations poured in across the electromagnetic spectrum. Optical telescopes tracked the light curve night after night. Ultraviolet observations from space telescopes captured the high-energy tail of the emission. Infrared instruments watched for thermal radiation from cooling debris. Spectroscopic observations decomposed the light into its constituent wavelengths, revealing the chemical composition of the ejector, their temperature, and their velocity. The expanding material was moving at roughly 10,000 kilometers per second, consistent with a powerful core collapse event. The spectra showed features typical of hydrogen-poor superluminous supernovae, meaning the progenitor star had shed its outer hydrogen envelope before the explosion, exposing the helium and heavier elements beneath. All of this was consistent with the magnetar engine model. A massive star strips away its hydrogen envelope, possibly through binary interaction or powerful stellar winds. The exposed core collapses. A rapidly spinning magnetar forms at the center. The magnetar pours energy into the expanding ejector, powering the extraordinary luminosity. The theoretical framework we built earlier predicted exactly the kind of light curve and spectral evolution that astronomers were observing. But consistency isn't proof. The light curve of SN 2017 EGM could be fit by a magnetar model, but it could also be fit by other models. And this is where scientific honesty becomes essential. Astronomers are careful people. They don't leap from observations to conclusions without considering alternatives. And there are alternatives. One of the most important alternative explanations for superluminous supernovae involves circumstellar interaction. This model proposes that the extraordinary brightness doesn't come from a hidden engine at the center, but from a collision between the supernova ejector and dense material surrounding the star. Here's how it works. In the final years or decades before the explosion, the progenitor star may have undergone violent episodes of mass loss, ejecting large amounts of material into the space around it. These eruptions can create dense shells or clouds of circumstellar material hovering at various distances from the star. When the supernova explodes and the ejector race outward at thousands of kilometers per second, they slam into this pre-existing material. The collision is violent. The kinetic energy of the fast-moving ejector is converted into thermal energy at the shock front where the two masses of gas meet. The gas at the interface is heated to extreme temperatures, and it radiates intensely. This radiation can be extraordinarily luminous, potentially matching or even exceeding the brightness of a magnetar-powered supernova, depending on how much circumstellar material is present and how close it is to the star. Circumstellar interaction has been directly observed in many supernovae, though not always at superluminous levels. Narrow emission lines in the spectra of some supernovae reveal the presence of slow-moving circumstellar gas being lit up by the collision. These emission lines are a clear diagnostic signature. When astronomers see them, they know circumstellar interaction is happening. In the case of SN 2017 EGM, the spectroscopic evidence was somewhat ambiguous. The early spectra didn't show the strong, narrow emission lines that are the hallmark of circumstellar interaction. This initially seemed to favor the magnetar model, but the absence of narrow lines doesn't completely rule out interaction. If the circumstellar material has been swept up quickly, or if it's distributed in a way that doesn't produce prominent narrow features, the spectral signature might be subtle or hidden. Some astronomers argued that a combination of mechanisms might be at work. A magnetar engine providing the bulk of the energy, with some contribution from circumstellar interaction adding to the luminosity. Nature rarely relies on a single mechanism when several are available. Another alternative is fallback accretion. In this scenario, not all of the material ejected by the supernova successfully escapes the gravitational pull of the central compact object. Some of the inner ejecta, the material closest to the neutron star or black hole at the center, slows down, stalls, and falls back onto the remnant. As this material falls inward, it releases gravitational potential energy, which can be converted into radiation. If enough material falls back, and if it does so over a sustained period, the energy released can be substantial. In the most extreme version of this model, the fallback is so heavy that it pushes the neutron star over the mass limit and it collapses further into a black hole. The newly formed black hole then accretes the infalling material, converting gravitational energy into radiation with potentially high efficiency. This can produce a luminous, sustained energy source that might contribute to a superluminous light curve. To understand why fallback accretion is taken seriously, consider the geometry of the explosion itself. When the supernova shockwave tears through the outer layers of the star, not every parcel of gas receives the same kick. Material near the poles might be launched outward with great force, while material near the equator or material sitting in denser pockets close to the core might receive a weaker push. Some of this inner material doesn't reach escape velocity. It climbs outward for a while, slowing under gravity's pull, and then reverses course. It falls back, like a ball tossed into the air that doesn't quite clear the rooftop. It rises, stalls, and returns. This fallback material carries gravitational potential energy. As it accelerates back toward the compact object at the center, that potential energy converts into kinetic energy. When the infalling gas reaches the neutron star surface, or spirals into an accretion disk around a newly formed black hole, the kinetic energy is released as heat and radiation. The process is remarkably efficient. Accretion onto a compact object can convert as much as 10 to 40% of the infalling material's rest mass energy into radiation. For comparison, Nuclear fusion in a star's core converts less than 1% of the hydrogen's rest mass into energy. Accretion is, pound for pound, a far more efficient energy source than fusion. The challenge with fallback accretion as an explanation for superluminous supernovae is that the process is difficult to observe directly. Unlike circumstellar interaction, which produces distinctive, narrow emission lines in the optical spectrum, and unlike the magnetar model, which predicts specific gamma-ray signatures as ejecta thin out, fallback accretion happens deep inside the debris, hidden behind the same opaque ejecta that conceal everything else at the center. Its contribution to the total luminosity is usually inferred by modeling. If the light curve can't be fully explained by a magnetar alone, or by circumstellar interaction alone, fallback accretion becomes a plausible additional ingredient. There's also a more dramatic version of this scenario. If enough material falls back, the neutron star's mass can be pushed above the maximum mass that neutron degeneracy pressure can support, roughly 2 to 2.5 times the mass of our Sun. At that point, the neutron star collapses further into a black hole. The newly formed black hole then continues to accrete the infalling material, potentially powering jets of matter and radiation that inject energy into the ejector from a completely different type of engine. This black hole formation scenario is speculative for most superluminous supernovae, but it can't be dismissed. The physics allows it, and in some cases, the light curves may be better explained by accretion onto a black hole than by a magnetar that survived. Fallback accretion is harder to diagnose observationally than either the magnetar model or circumstellar interaction. It doesn't produce as distinctive a spectral signature. Its contribution is often inferred indirectly by process of elimination when neither a magnetar model nor a circumstellar interaction model alone can fully account for the observed light curve. For SN 2017 EGM, the question of which mechanism dominated remained open for years. The optical light curve was consistent with a magnetar model. The spectral evolution was broadly compatible, but alternative explanations couldn't be definitively excluded. Astronomers needed another piece of evidence, something that could distinguish between the competing models, something that came from a different part of the electromagnetic spectrum, something that could reveal what was happening deep inside the expanding debris behind the optically thick ejector where the engine was hidden. And this is where gamma rays enter the story. Remember what we discussed about gamma ray leakage? As the supernova ejecta expand and thin out over months and eventually years, they become increasingly transparent to high-energy photons. Gamma rays that were initially trapped and thermalized inside the dense debris gradually find pathways out. These escaping gamma rays carry information about the energy source at the center. They're direct messengers from the engine room. If a magnetar is operating inside the ejector, the gamma ray signature should be distinctive. The magnetar's spin-down power produces high-energy photons with energies and a time evolution that differ from what radioactive decay alone would generate. As the ejector thin out, this magnetar-produced gamma radiation should become detectable by sensitive gamma-ray telescopes in orbit above Earth's atmosphere. Telescopes that can see the universe in a part of the electromagnetic spectrum that ground-based instruments cannot access because Earth's atmosphere absorbs gamma rays before they reach the surface. NASA's Fermi Gamma Ray Space Telescope is one of the most powerful instruments ever built for observing the high-energy universe. Launched in 2008, Fermi carries an instrument called the Large Area Telescope, or LAT, which surveys the entire sky in gamma rays continuously, building up exposure over months and years. It has been staring at the sky for well over a decade, patiently collecting photons, cataloging gamma ray sources, watching for transient events. But detecting gamma rays from a single supernova hundreds of millions of light years away is nothing like pointing a camera and snapping a photograph. Gamma ray astronomy operates under entirely different constraints than optical astronomy. Individual gamma ray photons are extremely energetic, but extremely rare. A bright star might deliver millions of visible light photons to a telescope every second. A distant supernova might deliver a handful of gamma ray photons per month, perhaps fewer. The signal is faint, embedded in a background of gamma ray emission from other sources, from our own galaxy, from the diffuse cosmic gamma ray background, from charged particles striking the detector and producing false signals. Extracting a meaningful detection from this noise requires patience and statistical care. The Fermi LAT doesn't produce a crisp image the way the Hubble Space Telescope does. Instead, it records individual photon events, logging the arrival direction, energy, and time of each gamma ray photon that strikes its detector. Over days, weeks, months, and years, these events accumulate. Researchers then analyze the data from a specific patch of sky, the location of the supernova, and compare the number of photons detected from that direction to the number expected from background sources alone. If there are more photons from the supernova's direction than the background predicts, and if that excess is statistically significant, meaning it's unlikely to have occurred by random chance, then the researchers can claim a detection. But the bar for statistical significance is high. In a field where you're searching many locations across the sky, random fluctuations can occasionally mimic a real signal. Astronomers must account for this, applying rigorous statistical corrections to ensure they're not fooling themselves. For SN 2017 EGM, this process involved accumulating Fermi LAT data collected over years from the supernova's position. The researchers examined different time windows, different energy ranges, and different background models. They tested whether the data were consistent with no gamma ray source at that location and found that the data favored the presence of emission. They then compared the detected emission's properties, its energy spectrum, and its timing relative to the original optical explosion, against the predictions of the magnetar spin-down model. This kind of analysis is painstaking work. It's not a dramatic moment of discovery where someone sees a flash on a screen and shouts that they found something. It's months of careful data processing, background modeling, systematic error analysis, and peer review. The result isn't a photograph of a magnetar. It's a statistical statement, a probability, a measured excess of photons that is consistent with a specific theoretical prediction. This is how cutting-edge astrophysics often works. Not with dramatic revelations, but with careful accumulation of evidence, each piece adding a small increment of confidence, each analysis sharpening the picture slightly. But when the statistics align with the theoretical predictions, when the number of photons, their energies, and their timing all point in the same direction, the cumulative weight of that evidence becomes compelling. Not proof in the absolute sense, but the kind of evidence that shifts the balance of scientific opinion and tells researchers they're looking in the right place. In 2026, a team of researchers analyzing Fermi LAT data published findings that added a crucial new dimension to the story of SN 2017 EGM. Their analysis of the gamma-ray data collected from the position of the supernova revealed evidence consistent with high-energy emission from the site of the explosion, emerging at a time and with characteristics that fit what the magnetar engine model predicts. This deserves careful framing because the language matters. The findings were described as evidence consistent with a newborn magnetar, contributing substantially to the extraordinary luminosity of SN 2017 EGM. Not proof, not definitive confirmation, evidence consistent with. This phrasing is precise and deliberate. In science, and especially in observational astrophysics, where signals can be faint and backgrounds can be noisy and systematic uncertainties can be significant, researchers are appropriately cautious about what they claim. What the Fermi data showed was that gamma-ray emission from the direction of SN 2017 EGM was consistent with the predictions of the magnetar spin-down model. The timing of the gamma-ray signal, its energy range, and its intensity aligned with what you would expect if a rapidly spinning magnetar were gradually losing its rotational energy, producing high-energy particles and radiation that were beginning to leak through the thinning ejector as they expanded and became more transparent. This is exactly the diagnostic signature we described earlier. The ejectors start dense and opaque, trapping the magnetar's energy and converting it into visible light. As months and years pass, the ejector expand and thin. Gamma rays begin to escape, and those escaping gamma rays show up in the data from a telescope designed specifically to see them. The researchers were careful to note that additional processes may also have contributed to the observed emission. Circumstellar interaction, fallback accretion, or other mechanisms might have played a role alongside the magnetar. The gamma-ray evidence supports the presence of a magnetar engine, but it doesn't rule out contributions from other sources. In astrophysics, multiple mechanisms often operate simultaneously. A supernova can be powered partly by a magnetar, partly by circumstellar interaction, and partly by radioactive decay, all at the same time. Disentangling these contributions requires careful modeling and continued observation. But the Fermi findings were significant precisely because they provided evidence from a completely independent part of the electromagnetic spectrum. The visible light observations had already suggested a magnetar engine was plausible. The gamma-ray observations now provided corroborating evidence from a different physical process entirely. When multiple independent lines of evidence point toward the same conclusion, confidence grows. It's not proof in the mathematical sense, but it's the kind of converging evidence that science relies on to build understanding. SN 2017, EGM also taught astronomers something broader about superluminous supernovae as a class. Its appearance in a large, metal-rich galaxy challenged the assumption that these events require special environments. Its detailed multi-wavelength observations provided one of the richest datasets ever collected for a superluminous supernova, and the Fermi gamma-ray analysis demonstrated that high-energy observations can serve as a powerful diagnostic tool for probing the engines hidden inside these extraordinary explosions. But here's what's equally important. SN 2017 EGM is one supernova. It's a case study, not a universal answer. And one of the most important lessons from the study of superluminous supernovae is that they may not all share the same engine. Some superluminous supernovae show clear spectroscopic evidence of circumstellar interaction, with strong narrow emission lines revealing the presence of dense material around the progenitor star. For these events, the collision between the ejector and the circumstellar material likely provides much or all of the extra luminosity. A magnetar may not be needed at all. Other superluminous supernovae show light curves that are better fit by magnetar models, with smooth, broad peaks and decline rates that don't match interaction signatures. For these events, a central engine seems more likely, and some may involve a combination. A magnetar providing sustained energy from within, while circumstellar interaction adds a burst of luminosity at specific times, perhaps when the ejector reach a particularly dense shell of pre-existing material at a certain distance from the explosion. The two mechanisms aren't mutually exclusive. They can coexist. They can complement each other. The real universe rarely offers simple, single-cause explanations for complex phenomena. This diversity is itself an important scientific finding. Superluminous supernovae are not a single uniform phenomenon with a single universal cause. They're a class of events that share the property of extreme brightness, but may achieve their brightness through different physical pathways. The magnetar engine is one pathway. Circumstellar interaction is another. Fallback accretion may be a third. And there may be mechanisms we haven't thought of yet. Understanding which mechanism dominates in which supernova requires exactly the kind of detailed, multi-wavelength, long-duration observational campaign that was carried out for SN 2017 EGM. Each superluminous supernova becomes a puzzle. The light curve provides clues. The spectra provide clues. The host galaxy provides clues. And high-energy observations from gamma-ray and X-ray telescopes provide perhaps the most direct clues of all, because they can peer through the thinning ejector and see the engine that drives the display. Future telescopes will make this kind of investigation increasingly powerful. More sensitive gamma-ray instruments, larger optical survey telescopes capable of detecting superluminous supernovae earlier and following them longer. Space-based ultraviolet and X-ray observatories with greater collecting area. Each new instrument adds another window, another perspective, another way to interrogate these extraordinary explosions and understand the physics hidden inside them. One of the most transformative instruments now coming online is the Vera Rubin Observatory in Chile. Its Legacy Survey of Space and Time, or LSST, will scan the entire visible southern sky every few nights, cataloging transient events with unprecedented speed and sensitivity. Current surveys find a handful of superluminous supernovae each year. The Vera Rubin Observatory is expected to increase that number dramatically, potentially discovering dozens or even hundreds per year. Each discovery is another data point, another puzzle, another chance to compare the magnetar model against alternatives. With a larger sample, patterns will emerge. Astronomers will be able to study whether superluminous supernovae in different types of galaxies behave differently, whether there are correlations between the peak brightness, the decline rate, and the host environment, whether the gamma-ray signatures vary systematically from event to event. Statistics will sharpen. Rare subtypes will become identifiable. The current picture, assembled from a few dozen well-studied events, will be replaced by a landscape mapped from hundreds. Gravitational wave detectors offer another entirely independent window. Instruments like LIGO and Virgo detect ripples in spacetime produced by cataclysmic events. A core collapse supernova in a nearby galaxy might produce detectable gravitational waves. If a rapidly spinning neutron star forms in the collapse and wobbles slightly as it spins, it could emit a continuous gravitational wave signal, that persists for seconds or minutes. Detecting such a signal simultaneously with the optical and gamma-ray signatures of a super-luminous supernova would provide direct, unambiguous evidence that a rapidly spinning compact object exists at the center of the explosion. It would move the magnetar model from strongly supported to essentially confirmed for that individual event. Next-generation X-ray telescopes will also contribute. Instruments with larger collecting areas and better angular resolution will be able to detect X-ray emission from superluminous supernovae at earlier times, catching the transition from opaque to transparent ejecta with finer time resolution. This will allow astronomers to measure exactly when and how quickly the ejecta become transparent, constraining the mass and velocity of the debris, and by extension, the properties of the progenitor star and the engine at the center. Each of these instruments probes a different aspect of the same physical system. Optical telescopes see the reprocessed visible light. Gamma-ray telescopes see the leaking engine radiation. Gravitational wave detectors feel the space-time vibrations of the spinning remnant. X-ray telescopes catch the transition in between. Together, they offer something no single instrument can provide. A complete multi-messenger portrait of a superluminous supernova, from the surface of the ejecta all the way down to the magnetar at its heart. The era of understanding these extraordinary explosions is just beginning. And so we arrive at the heart of our story. The idea that has been building since we first asked the question in the opening moments of this journey: how can a dead star make a supernova brighter? The answer is extraordinary in its elegance and profound in its implications. When a massive star dies, when its core collapses and its outer layers are blown into space, the death doesn't end the story. The collapse itself creates something new. A compact remnant, a neutron star, crushed into an object barely 12 miles across, but containing more mass than our sun. Conservation of angular momentum spins this remnant up to hundreds of rotations per second. Under the right conditions, a convective dynamo in the first few seconds of its existence amplifies its magnetic field to levels that surpass anything else in the known universe. The remnant becomes a magnetar. This magnetar holds in its spin a reservoir of energy so vast that it rivals or exceeds the energy of the explosion that created it. Through the physics of magnetic braking, through the relentless drag of an ultra-strong magnetic field rotating at extreme speeds, the magnetar converts its rotational energy into an outgoing torrent of accelerated particles and high-energy radiation. This energy floods outward into the dense, expanding ejecta that surround the magnetar on all sides. The ejecta absorb this energy. They trap it. They thermalize it. Through repeated scattering and absorption events, the fierce gamma rays and X-rays produced by the magnetar are ground down into softer, lower energy radiation, visible light, the kind of light our eyes can see, the kind of light our telescopes can measure. The ejecta glow from within, heated by the continuous energy input of the spinning dead star at their center, shining far brighter and far longer than the radioactive decay of nickel-56 and cobalt-56 could ever sustain. A dead star is making the supernova brighter. A corpse is powering the explosion that created it. The stellar remnant, which by every conventional measure has nothing left to give, turns out to carry the largest single energy budget in the entire system. And it spends that budget generously, pouring its rotational energy into the expanding debris, sustaining a display of light that can outshine 10 billion suns. As the ejecta expand and thin, gamma rays begin to leak through. These escaping photons carry the fingerprint of the magnetar engine, allowing astronomers with the right instruments to detect the hidden power source and confirm that something inside the supernova is doing what no nuclear reaction can do at this stage. Something is adding energy from within. Something created by the death itself. Something that turns the end of a star's life into the beginning of the most luminous chapter of its story. SN 2017. GM gave us one of our clearest glimpses of this process in action. Its extraordinary brightness in a surprising host galaxy drew the world's attention. Its multi-wavelength observations over months and years built a detailed portrait of an engine-driven explosion. And the Fermi gamma ray analysis, published in 2026, provided evidence from the high-energy universe that corroborated what the visible light data had been suggesting all along. A magnetar, newborn and furiously spinning, contributing substantially to a supernova that refused to follow the rules. Not every superluminous supernova is necessarily magnetar-powered. The universe is more creative than any single model. Circumstellar interaction, fallback accretion, and perhaps mechanisms not yet imagined all play their roles in different events. But the magnetar engine model remains one of the most compelling and well-supported explanations for the most extreme stellar explosions ever observed. It connects the physics of neutron stars, magnetism, angular momentum, and radiative transfer into a single coherent narrative that turns a dead star into the most powerful engine in its own explosion. And there is something deeply moving about this idea. A star lives for millions of years, burning through its nuclear fuel, fusing element after element in a desperate struggle against gravity. It exhausts its options. It reaches iron. The core collapses. The star dies. By every measure, the story should be over. The fuel is gone. The nuclear reactions have ceased. The star is dead. But the death creates something the star never had while it was alive. A compact remnant spinning faster than anything the original star could have imagined, carrying a magnetic field stronger than anything the living star ever possessed, holding a reservoir of energy that dwarfs the visible output of the original explosion. The death doesn't just end the star, it transforms it. It distills millions of years of stellar evolution into a 12-mile sphere of nuclear matter, rotating hundreds of times per second, wrapped in magnetic fields of almost inconceivable intensity. And from this remnant, from this crushed core that will never fuse another atom, energy pours outward, not from nuclear reactions, not from chemical processes, but from the sheer momentum of collapse itself, converted through magnetism into a sustained flood of power that brightens the expanding debris and sustains a light show visible across hundreds of millions of light years. The dead star lights up its own explosion. The corpse outshines the funeral. The end becomes a new beginning. And somewhere out there, right now, in a galaxy we may never have looked at, a massive star is reaching the end of its fuel. Its iron core is growing heavier. The final hours are ticking away. Soon, the core will exceed the limit. It will collapse. The outer layers will be torn apart, and deep inside the expanding fireball, a magnetar will be born, spinning furiously, wrapped in impossible magnetism, carrying in its rotation more energy than the explosion itself. And for weeks, for months, that dead star will make its supernova brighter. It will hold the light up against the darkness. It will burn with borrowed energy, energy borrowed from its own angular momentum, and it will create one of the most luminous events the universe has ever produced. Because even in death, even in the final collapse of a star that has nothing left to give, the universe finds a way to create something extraordinary. A dead star making light, a corpse refusing to go dark, a stellar remnant born in destruction, turning that destruction into the most magnificent display of radiance in the cosmos. That is how a dead star makes a supernova brighter. Not through any new source of fuel, not through any violation of physics, but through the beautiful, inevitable consequences of conservation laws and electromagnetism, through spin and magnetism, and the stubborn refusal of a collapsed core to surrender its energy quietly. The star dies, and then it shines,